I never quite know where to put my things for this PowerPoint. Okay, this video is going to cover section 2.2, which really has 3 parts. We're going to talk about the idea of a limit. Then we're going to talk about one-sided limits, and then we're going to talk about infinite limits. You ready? Let's go. Okay, section 2.2, the idea of a limit. The first example is, let's consider this function. We've got a rational function of x minus 2 over x squared minus 4. The first thing we want to do is look at the domain of this function. Because it's a rational function, okay, because it's a rational function, we know that the denominator cannot equal 0. Well, the denominator is x squared minus 4. So we know that that bad boy cannot be equal to 0. So we have to take this piece right here and solve it for x in order to figure out what values of x don't work. So x squared minus 4, we can do a couple of things. It's not linear, so I don't want to solve it using linear methods, okay? I can really solve this 2 ways. I can factor it. I can say x plus 2 and x minus 2 don't equal 0. And then that gives me that x cannot equal negative 2 or 2. Or I can take x squared minus 4 and add 4 to both sides. So I get x squared can't equal 4. Then I can take the square root. And the thing to remember about the square root is if I take the square root here, I've got an even power here. That means that what could be the square root of a positive 4 is plus or minus 2. Either way, for this domain, we get the values that x can be anything, but it can't be negative 2 or positive 2. Darn it, I wrote over it. I tried to not. Okay. Just focus over here. All right, so the next part when we're considering this rational function, the function f of x is not defined at x equals 2. So we know that that's one of the points that it's not defined at. So then let's take a look at how does the graph f of x behave near x equals 2. All right. Sounds like someone's doing construction in the other room. Oh goodness. If you hear that noise, it's not me. Okay, so let's take a look at how the function f of x behaves near x equals 2. First thing we want to do is draw the graph. You can plug this into your graphing calculator, or you can use an online graphing function. But this is what our graph is going to look like. Keep in mind, here I've got my grid. I've got this function here and function here. We can see at negative 2 that I have a vertical asymptote, but if you zoom in real close at 2, you can see that it doesn't exist there. So how does f of x behave near 2? Well, there's a hole. Okay, so if you kind of follow that graph there, you look, it does approach it, but here at 2, there's a little hole. Well, let's see if we can prove that. Depending on your settings for your graphing calculator, you may not be able to tell that there's a hole in that function. So the other way to check it out is to look at the table. So what we're trying to find is what happens near the hole in the domain at x equals 2. We want to know what's going on right here, okay? Right now it's a big question mark that I just scribbled over. You're welcome. So what I'm going to do is I'm going to plug in values into my table that are very, very, very close to 2. I'm going to plug in values that are really close to 2 but larger than 2. And I'm going to plug in values that are really close to 2 but smaller than 2. And I'm going to use my graphing calculator to do that. Okay, once I've plugged all those values in, and kind of note what values I plug in there, notice what's happening. So basically start far away and then look as we hone into 2. What are those output values doing? Okay, same thing here. Look at your graph. Get close to 2. What are your output values doing? So now we can kind of put it together. Looking at the table of values, as I get closer and closer and closer to 2 for my x value, look at what is happening to my y value. Same with the graph. As my x value gets closer and closer and closer to 2, look at my output value, okay? We can kind of look at this right here. We can say, okay, if we were to trace that back to the y-axis, what is that value there? As x is approaching 2, f of x is approaching a quarter, or 0.25. Another way to say this is that the limit of f of x as x approaches 2 is 0.25. What does that mean, the limit? Well, think about this. If we plug in 2, we're just going to get an error because that's a hole in the domain. So if we plug in 2, the actual value of f of x doesn't exist. But if we look at what f of x is getting close to as x is approaching 2, we see that it's a quarter, all right, or 0.25. Mathematically, we write this a couple of different ways. We use the arrow for approaching, okay? So here we're saying f of x is approaching 0.25 as x is approaching 2. We can also write it another way. We can say that the limit of f of x as x approaches 2 is equal to 0.25. Or we don't have to use the function notation. We can actually write the function. We can say that the limit of x minus 2 over x squared minus 4 as x approaches x equals 2 is equal to 0.25. It's quite a mouthful, isn't it? So here we approach a definition. We say that the limit of f of x equals L as x approaches to a. And then we write it like this. The limit of f of x equals L as x approaches a. This is true if we can make the values of f of x arbitrarily close to L by taking x to be very close to a, but not equal to a. So in other words, getting really, 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 really close to that value, but not equal to that value. That's how we can find the limit. Let's look at this example here. Let's consider the rational function of sine of x over x. And let's find the limit of f of x as x approaches 0. In other words, we could write it like this. Find the limit of sine of x over x as x approaches 0. Okay. Here's the essential things we want to look at. And you don't really have to do them in any order. All of them help. But I do suggest starting with a graph. Start with a graph. So the first thing you're going to do is graph that function. Then you're going to look at what's the domain of that function. And then you're going to look to see, is f of x defined at x equals 0? Then you create a table. Keep in mind that since we're looking for where the limit as x approaches 0, our table then is going to be built around 0. So in a way, I always start my table with this little value right here, and the rest of these I fill in. And notice what I'm doing is I'm basically adding a 0.01 or subtracting a 0.01 each time, or a 0.001 or a 0.1 each time as I move farther and farther away. Okay, if I draw the graph of sine of x, sine of x over x is going to look like this. Note that there is, and it's hard to see it, not there, right there, if you were to zoom in on this function, you would see that there's a little hole there that I didn't draw well at all. So we're going to try that again. There we go. Okay. This function basically looks like this. It's hard to trace that. Okay, so this is what my function looks like. Once I've looked at the graph of it, I can also look at the equation and say, okay, what's the domain? Well, again, this is a rational function, and I can see that x is in the denominator. So since my denominator can't be equal to 0, that means that x can't equal 0. Then when I look at this, well, is f of x defined at x equals 0? It definitely isn't defined at x equals 0. Okay, my order was off on my animations a little bit. But when I create a table using my graphing calculator, keep in mind this is what I'm going to do. I'm going to build that table around 0. So I'm going to go slightly bigger than 0 each time, and then slightly smaller than 0 each time. And then what I'm going to do is I'm going to look at these values as I get really, 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 really close to 0. Notice what the output values are doing. Now, I don't know about your graphing calculator, but my graphing calculator doesn't have a whole lot of room on it. So when I get to values that are really close to 0, what it'll actually do is it'll give me a value that's like approximately 1. It'll round it. And now, if I look at it, it's like 0.99999. I think it's 6345698, blah, blah, blah. Okay? But when you look at it in the table, it'll actually say 1. However, if you look over here, which I can't draw an arrow in the right spot. There we go. We'll try that. If I look over here when x is equal to 0, I get an error message. Because f of x is not defined at x equals 0. Sine of 0 is fine on the top, but 0 in the denominator is not okay. So it's an error. But also, same thing here. I look as I get closer, I'm starting off at 0.841, 0.998, 0.99998, 0.9999999, and then we get over here again where this value is so close to 1 that the calculator will round it to 1 for you. So then what can I say? What can I say? What is the limit of this function as x is approaching 1? Again, remember, we're not looking to see what it is when x is equal to 0. I said that wrong. What is the limit of sine of x over x as x is approaching 0? I said the answer. What is it? Yeah, what's the output approaching as the input is approaching 0? Yeah, it's approaching 1. So, considering all of our work, the limit as x approaches 0 of sine of x over x is equal to positive 1. We could see it in the graph. We could see it in the table. Now we're going to look at one-sided limits. So we just introduced the concept of a limit. Now what we're going to do is look at the concept of a one-sided limit. We're going to have two sides, a left-handed limit and a right-handed limit, okay? And think about that. Doesn't that make sense? I'm looking at the values of x as it approaches from both sides, and I'm going to have a left-hand limit and a right-hand limit. So the left-hand limit is the limit of f of x at equals L as x approaches to A. And that's how we're going to write it. We're going to write it as x approaches A from the left. Okay, see that little minus sign? Think of that from the left, but also think that that's where it's coming in from the smaller values. And if we can make the values of f of x arbitrarily close to L by taking x to be very close to A and less than A. So in other words, we're approaching from the negative side, we're approaching from the smaller side, the side that's less than A. In the opposite direction, the right-hand limit. we say the right-hand limit of f of x equals L as x approaches to A, and we write it like this. The limit as x approaches A from the right of f of x is equal to L. And we do this if we can make the values of f of x arbitrarily close to L by taking x to be very close to A and greater than A. So in other words, we're approaching from the positive side of things. We're approaching from the positive numbers. So let's look at this function here. The function f of x is equal to the absolute value of x divided by x. And we're going to find the left-hand limit and the right-hand limit of f of x as x approaches to 0. So first things first, let's look at a graph. Here we've got this graph here. I don't know if you can see it. Okay. Can I get close? It's always so hard to tell. Here, I'm just going to exaggerate it. There's a big open dot there. And here. No, yeah. It's a big open dot there. All right, so here's my graph of the absolute value of x over x. It's basically two straight lines that crash into the x-axis or y-axis and cease to exist, okay? So looking at that graph, I can kind of have an idea of the different limits that I have going on here. So as I look at that graph, I can have an idea of the limits that are going on here. All right, let's look at the left-hand limit. All right, for the left-hand limit, I am going to look at the limit as x approaches 0 from the left of the absolute value of x over x. And I want to figure out what's that value. So here is 0. Here the value is smaller than 0. So my limit as x approaches 0 from the left, what are the output values here? Yeah, it's -1. So for this function, it's going to be equal to -1 for the limit. I forgot I brought this little tool with me. Okay, so here it is. Oh, I can't have it too close, otherwise the light will get rid of it. As I'm approaching this function, approaching the x value of 0 from the left, I can see that f of x is equal to -1. If you don't believe me, graph it on your calculator, take a look at it. The other thing also is you can plug values into a table. Think about that. What values in a table are coming from the left side? So of 0. So here, right here, we have x equals 0, right? So what's something that's really close to 0? Well, you can go not that close to 0, but -1, right? Now, closer than that is going to be -0.1, and then -0.01, and then -0.001, and then -0.0001. Do you see what I'm doing? I'm getting closer and closer to 0. Okay, now let's look at the right-hand limit. Sorry for my squeaky marker. It's protesting. Okay, so we're going to look at the right-hand limit. We're going to look at the limit as x approaches 0 from the right-hand side. The right-hand side is the positive side. We're going to look at how this function, absolute value of x divided by x, what value it approaches as x approaches 0 from the right. Okay, so same thing. Here I'm going to approach, looking at the x values, I'm going to approach 0 from the right. And then I look to see, well, what are those output values? And the output value of this function is going to be +1. Now, something to notice here. Okay, here's my left-hand limit. Here's my right-hand limit. Notice they approach different values. Even though they're both approaching 0, the function is approaching different levels. Interesting, huh? Notice how this example we just did is different than the one that we did first. The one that we did first, everything was approaching in the same value from the left and from the right. When we look at these one-sided limits, the idea is we want to look at what's happening from the left, what's happening from the right, because the limit of the function f of x exists only when the left and the right-hand limits coincide. They have to be the same. So here we've got this theorem. The limit of f of x as x approaches a is equal to some value L if, which means if and only if, the limit as f of x, or the limit of f of x as x approaches a from the left is equal to L, and the limit of f of x as x approaches a from the right is also equal to L. In other words, like what I was showing you before, let me get them in the right thing. So if I'm approaching from the left and I'm approaching from the right, and they're not approaching the same value, then the limit doesn't exist. Now, the left hand exists and the right hand exists, but because they're not coinciding at the same value, the actual limit doesn't exist. But like in our previous problems, if we're doing stuff from the left and the right, and then they meet at the same spot, then we can say that that limit exists. Let's see what I'm talking about. So I've got 3 examples here where I'm showing that the limit does exist. So here, look at this function as x is approaching a. Coming from, my light's not quite shiny enough. Okay, I gotta go back here. This is all a process. Okay, so I've got my left hand limit and my right hand limit. Here is x approaches a. So what happens as I get closer to a, my function's doing what? Going off into infinity. That's right. Are they both going into infinity? Yeah. So the limit exists. Okay, now let's look at a different type of function. Again, here's some value, x equals a. I'm going to look what happens to the function as x gets closer to a from the left, and what happens to the function as x gets closer to a from the right. And I got to back out because apparently the graph is like the same color as me. It disappears a little bit. Okay, so what's going to happen? When I get close, I'm going to trail. Boom. They meet in the same point, right? They're not going off into different directions. They're meeting in the same point. The left-hand limit is here, whatever I'm drawing there. Right there. If I were to trace that over, this would be that limit value. This would be that L. Because my left-hand limit is the same as the right-hand limit. Even though, if you look at that graph, there's a hole there. You can't see what x is, or what f of x is equal to for x equals a. Then we've got a different graph over here. Notice there is no hole in it at x equals a, but same thing. If I am approaching from the left, I can see I'm approaching this value. And here as I'm approaching from the right, I can see that the function is approaching this value. Okay, so all of these are examples where the limit exists. Isn't that good? Right? Math is so wonderful. It gives us definitions for things like existence. Let's look at an example of one-sided limits and limits in general. Remember, there's the plain Jane limit, okay? The one as x approaches a. And then there's the left-hand limit. The one as x approaches a from the left. And then there's the other limit as x approaches a from the right. I'm worried that you can't see those and that they're not big enough. So I'm going to make them bigger. Just a second. Be right back. Thinking I would wear sunglasses to make this easier to see. That doesn't really work. Okay. All right, I'm back. It's very weird to work in front of these lights and then go do stuff over there. But we can do it. Okay. So let's look at this first limit here. F of x, I don't have a function or an equation for f of x, but I do have a graph for f of x, and this is it. It's just some arbitrary graph made up for you. So let's take a look at this. If I've got the limit of f of x as x approaches 1 from the left. So first of all, here's your x-axis. Find x equals 1. That's this bad boy, right? That's this guy right here. So what I'm going to do is I'm going to take this function and I'm going to follow this function until it gets to x equals 1. Pow. Okay? Going over here to this. And I see that the output as I'm approaching 1 is equal to -2. So this one's going to give me -2. All right, let's take a look at the next one. B. Oh, I made it bigger, but you still can't see this. It's supposed to be plus. Dang it, nabbit. We'll just... That's supposed to be plus. Okay, so now I'm going to look at the limit of f of x as x approaches 1 from the right-hand side. So here's 1, right? Here's 1. Now from the right-hand side, that's this guy, going over this way, right? But I'm going to follow f of x until I get to x is 1. And when I follow that, it approaches up here. So approaching from the right, what's that output value there? Yeah, it's 1, 2, 3. So this is going to be equal to 3. Notice the difference in the questions, right? This one's the left-hand limit. This one's the right-hand limit. This one's just the limit. So this is asking me, what's the limit of f of x as x approaches 1? So remember, the plain Jane limit, without any left or right connotations, only exists if the left and right bad boys do what? Yeah, they gotta meet. Do they meet? Are they meeting? No, there's a divide between them. So what do we say about this limit? Well, we say it does not exist. But we don't write does not exist. We just write DNE, because who's got time to write that stuff? Okay. Next problem, and this is like from a previous algebra course. It's asking us what is f of 1. Okay, so here's my function. It's graphed. Here's x equals 1. If I want to know the output of f when f is 1, or sorry, when x is 1, what I need to do is look, okay, here at x equals 1, which one's filled in? Well, this dot's empty, so that's not it. This dot right here, that is filled in. So that is my value of my function at 1. And that's -2. Let's try the next couple of sub-problems. Erase my work real quick. It's funny, the orange doesn't quite write as well, but it's easier to erase, which makes me like it. But the blue is so pretty and the green is so pretty. Okay. So now let's look at this next question. This is the limit of f of x as x approaches 5. Yeah. All right. So as x is approaching 5, where's 5? So here's my x-axis, right? Here's my x-axis. Here's my x's 1, 2, 3, 4, 5. That's this guy right here. Okay. And so we're going to look at this. Okay. All right. So notice that there's no specific left or right clarification on this limit. We're just looking as x approaches 5. So that means that the left-hand side has to be the same as the right-hand side. And are they? If I were to follow the path of f of x as x is approaching 5, do I see that they're the same? I do. I do. They're approaching the same value, right? Okay, so this is 1, 2, 3, 4. So as f of x, as x is approaching 4, this is not like a board. I can't just use my fingers. As x is approaching 5, f of x, the limit of f of x, is equal to 4. That doesn't mean that f of x is equal to 4. It means the limit is equal to 4. So down here, again, we'd have a problem from like a previous class, but still important. This is the value of f of x at x equals 5. Okay? So if I look here at the value of f of x as x equals 5, there's a hole there, right? There's nothing there. So f of x doesn't actually equal 4. This one also does not exist. It appears to be, there's a hole there, right? Okay, so can't make any assumptions about that. If you don't get it, rewind it. Watch it again. But also notice that there's a difference between the left-hand limit, the right-hand limit, a regular limit with no left or right-hand connotations, and then just values, function values at particular places in this function. All right, our third subcategory section of section 2.2 is infinite limits. All right, here are the definitions of infinite limits. Well, actually, I'm sorry. Before I get there, I want to specify. These are not limits to infinity. These are infinite limits. This is what happens when your function approaches infinity, or when your function approaches negative infinity, like in a vertical asymptote or something. Okay, so definition. We're going to let f be a function defined on both sides of a, except possibly at a itself. Okay, so it may not exist actually at a, but it exists from the left and right hand side. Then we say the limit of f of x as x approaches to a is infinity. And we write this. The limit of f of x as x approaches a is infinity. I promise it's just allergies. Now, if we can make the values of f of x arbitrarily large by taking x to be very close to a but not equal to a. This last part, look at this math speak. It's always so combobulated, isn't it? In other words, when we plug in values that are getting very, 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 very close to a on the left hand and the right hand side, we notice that f of x is shooting off into space, going up into infinity. Okay, similarly, we look at the limit of f of x as x approaches to a is negative infinity. Okay, and we write this, the limit of f of x as x approaches a is equal to negative infinity, if we can make the values of f of x arbitrarily large and negative by taking x to be very close to a, but not equal to a. In other words, we're approaching x to a from the left-hand side and the right-hand side, and the function is going down, right? Okay, let's take a look at some examples of that. So for this one right here, what do I notice? As I'm doing the left and right hand values, I can say for this one, the limit as x approaches a of this function is equal to positive infinity. I need some water. These lights are bright and hot and hydrating. Okay, Next, let's take a look at this one. Here's this function. Here's my left approach to A. Here's my right approach to A. What do I notice? Yeah, this one I can say the limit as x approaches A of f of x is equal to negative infinity. Right? What about this one? What can I say about this one? Well, if you think you know, pause it and write it down. Then unpause it and let's see if you're right. I call that that process like checking your instincts. Sometimes what we think is right, we think we know it, and that's our instincts. Sometimes they're right, and it's always good to know that. Okay, so if you think you know, pause it, write it down. If not, just do it with me. Ready? Okay, we're either checking your work or you're doing it with me right now. Okay, so for this one, what can we say? The limit as x approaches A of f of x, what can we say about it? Well, here's my left-hand limit. I'm approaching A and I'm going down this way. Here's my right-hand limit. I'm approaching A and I'm going up this way. So what do I say about the actual limit? The limit as x approaches A. Yeah, that little stinker doesn't exist, does it? So the limit of f of x as x approaches A does not exist. However, what's the limit as x approaches A from the left-hand side of f of x? So approaching from the left-hand side, it's negative infinity. Good. I can also identify what? The limit of f of x as x approaches A from the positive. You can't read that. Dang nabbit, I went too low. I'm going to do it here. Limit as x approaches A from the right-hand side of f of x. So here's my right-hand side. Good. It's going off into positive infinity. Ignore that. These are infinite limits. Let's play with them a little bit more. Okay, for this next example, we're going to find these infinite limits and we're going to use graphs. I gotta say this, when you're doing a limit, graph it. If you don't know what the graph looks like, plug it into your graphing calculator or use an online graphing calculator like Desmos. Those things are wonderful. Desmos being D-E-S-M-O-S. I believe it's .com. And just hit start graphing, okay? I use that a lot to make my graphs here. Okay, so we are going to look at this function here. Graph the 5 over x minus 3 squared. And you're going to see a graph that looks like this. Sorry. You're going to notice here at x equals 3, you have an asymptote. And the function does this. Okay, so the limit as x approaches 3. What's my left-hand limit going to? Infinity. What's my right-hand limit going to? Infinity. So we can say that the limit of this function as x approaches 3 is equal to positive infinity. Let's look at the next one. Again, start with a graph. So squeaky. Again, because of the denominator, we do have a vertical asymptote at x equals 3. We also, whether or not you know this part, we have a horizontal asymptote at y equals 1, and it looks like this. All right, so this is our function here. So keep in mind, note what they asked for. I've got 3 from the left of this limit and 3 from the right of this limit. Notice I didn't just ask for 3. If I ask for the 3 for this function, I actually can say what? Okay, here's my left-hand side. Here's my right-hand side. These bad boys are going in opposite directions. So the limit as x is approaching 3 doesn't exist, but the left-hand limit does. So as x is approaching 3 from the left, the function is going down, 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 forever and ever, ever, amen. So this thing has a limit value of negative infinity. Then let's look at the right-hand limit. As this function is approaching 3 from the right, I can see that this is going up and up and up forever and ever and ever. So this is, whoops, going to be equal to positive infinity. Get it? This is so weird teaching in a filmed format. No one can ask me questions. That's why we have Zoom meetings, though. So if you do have questions for me, make sure to come to your Zoom meeting. The other thing is this. Other than a graph, you can also use a table of values. Keep in mind, for this function right here, I'm approaching 3 from the left and the right. So I would plug in values very, 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 very close to 3. For example, I would plug in from the left side, I would plug in 2.9, then 2.99, then 2.999, then 2.999, right? And I would see what happens. And then if I'm approaching 3 from the left, from the right, I would say, okay, try 3.1, then 3.01. Then 3.001, 3.0001, and keep on going. Okay? So here, if I'm just looking at the left-hand values, I'm plugging in values smaller than 3. Here, for the right-hand values, I'm plugging in values larger than 3. So you can use your graphs, but just in case you don't trust what you see, you can always verify it with a table. All right, so extra examples. What I'd like you to do at this time is pause the video, try this on your own, and then see if you get the right answer. Again, test your instincts. You want to find out if your instincts, after watching this and trying a couple of problems, you want to know if your instincts are good or if they're crap, right? Because if they're crap, that's what the studying is going to compensate for. It's going to replace your crap instinct with a good instinct. If your instinct is good, that's good. You want to know that. And then, of course, do all your homework to solidify that good instinct, right? That's all really math is you try stuff and either it's good or it's crap. You never know. You don't know, right? Or, you know, I shouldn't say that. It's not just two options. It could be good. It could be crap. It could be somewhere in the middle. And you just need to like take your way to wind yourself over to good, right? Or it could be excellent. I need some water and a snack. I'm getting a little loopy. Okay, extra examples. Again, pause, try it on your own, see if we can do the same thing. Ooh, but wait, before you pause, let me say this. Start with a graph. Graph this function, take a look at what you have. What you're trying to figure out is determine values for a for which the limit as x approaches a of f of x exists, okay? So it's a lot of values. This is what we call a piecewise function. Remember this from your previous classes. This is something, I like to think of this as like the relay race of functions, okay? So the function that runs the first leg is 1 plus sine x, and he runs this leg as long as x is smaller than 0. Then the next leg of the race is run by cosine of x, right? She's quick. And she's going to run as x goes from 0 to pi inclusive. And then sine of x is going to run the last leg, which is the forever leg, as x is greater than pi. Okay? All right, so pause it, see if you can do it. Otherwise, just watch along with me. As I said before, we're going to graph it. Always graph it. Okay? It's a piecewise function, so this is what you should see. 1 plus sine x is going to be here as x is smaller than 0. So that's this whole graph, okay? So here's 1 plus sine x. I ran into something. It's going over here. And then my next leg is my cosine of x, and that's from 0 to pi. And then my last leg, and sorry I've got them in the wrong order here, is sine of x, and that's going to run the very last leg. We're looking for values of a where the limit exists. And keep in mind, the limit exists all these spots where the left and right hand limits are always going to meet each other. So look at all these things meeting each other. But specifically, because there are two handoff points, there's a handoff point here. Whoops, sorry. There we go. I'll just draw a little arrow like that. Here at x equals 0, 1 plus sine of x passes off to cosine of x. And notice, here comes sine of x, 1 plus sine of x. Here comes cosine of x, and they both meet in the same spot. So these all have limits. So specifically, x approaches 0 is a limit that works. Then we get over here to pi. Notice what happens at pi, okay? So line up my bad boys. Here I'm coming from the left side. Here I'm coming from the right side. What do we notice? Yeah, they don't match up. So does the limit exist at as x approaches pi? Yeah, as x approaches pi, the limit of f of x does not exist. Now, the limit as x approaches 0 of f of x does exist, and specifically, it's 2. Oh, sorry, no, it's 1. I didn't mark this up. Yeah, 2's right there. Yeah, no, it's 1. So this one does exist, and it's 1. Everything else exists as well. The only one that doesn't exist is as x approaches pi. So now let's take a look at our next example. I want you to sketch a graph that has all of these attributes, okay? There's a lot of them. The limit of f of x as x approaches 0 has got to be 1. The limit of f of x as x approaches 3 from the left has got to be -2. And the limit as x approaches 3 from the right has got to be +2. F of 0 has got to be -1, and f of 3 has got to be 1. You ready? Let's do it. Okay. Again, you can pause this, try it on your own, and see if you get it. Test out your instincts. If not, that's okay. You can watch me and then do this again. I'll give you a hint, though, before you pause it. Start with the exact values. Start with your function values. Those are the ones you want to start off with first, okay? All right, either pause it and draw it, or watch with me. Okay, so I'm going to start with my function values first, the plain Jane ones. I'm not going to start with the limits. Start with your plain Jane values. So I've got f of 0 equals -1. Well, that's right here. Need to make some space for the orange, or the orange will get ooky. Okay, f of 0 equals -1. Next, f of 3 is equal to +1. Okay, so check and check. Next, let's go with this first limit right here. Now this limit is as x is approaching 0. So this limit is as x is approaching 0 from the left and from the right, and it's equal to +1. So as I'm approaching x equals 0 from the left and the right, the function is approaching positive 1. Not this negative 1 down here, but positive 1. So since I know it's not equal to 1, I'm going to put an open dot there. Okay? Now, let's approach x equals 0 from the left. So we're going to approach in this direction. So in other words, my left-hand limit here as I'm approaching 0 is going to be a positive 1. So I can have my function do whatever I want as long as it comes up to positive 1. So I'm just going to draw that guy. All right, now there's also this. I need to be approaching 1 from my left-hand side too, right? So I'm just going to draw a little tail because I'm going to connect it. It's like a very advanced version of connect the dots. So I'm going to connect it, but I also got to figure out what's going on over here. Okay, so far this guy is taken care of. Now let's look at the next one. And then I connect it this way. As I'm approaching 3, okay, from the left-hand side, but also keep in mind, I'm approaching 0 from the right-hand side. So I got to make sure that these bad boys connect. But this limit here, as x is approaching 3 from the left, is equal to negative 2. So that's where my open dot goes, and I've got that one covered. Now let's do the next one. The limit of f of x as x approaches 3 from the right is positive 2. So here's 3, and I want to approach 3 from the right, and here's positive 2. So I'm going to do an open value there, because again, f of 3 is equal to 1. So when I come in from the right, I'm going to approach this guy, and you can have this do whatever you want, as long as you're going to positive 2. Here is your last extra example. We did one like this earlier, so I definitely want you to pause the video and see if you can answer all of these and test out your instincts. As x is approaching negative 1 from the left, we can see, okay, x is approaching negative 1 from the left. That means that f of x is approaching positive 1. Okay, it's approaching that point right there, and that point has a y value of positive 1. So this one here, positive 1. Let's look at b. As x is approaching negative 1 from the right side. Okay, from the right side, that's that plus. Again, I'm approaching from the positive numbers. So here I am, choo-choo-choo. I always think this is kind of like a choo-choo train, going on the tracks of h of x. I'm going as negative 1, approaching negative 1 from the left, but I have to follow the train tracks of h of x, and this thing is taking me down to negative 2. So this one's going to give me negative 2. You can't see that. I'm just going to put it over here. Negative 2. Sorry, it's too far over. Next one. What's the limit of h of x as x approaches negative 1? They're approaching in the same spot? No. So what do we say about this guy? You don't have to write equal does not exist. You could just write DNE does not exist because we don't have time to write the whole thing. And then next we're looking at what is h of negative 1? Well, h of negative 1 is where it's filled in at negative 1, and that's there at 1. So this one I can squeeze in. That equals 1. All right, next problem. The limit of h of x as x approaches 3 from the left. So here's 3, and here's my left, and I'm going to approach 3 from the left, but I have to do it following the path of h of x. So when I do that, I can see that that's going to give me 2. Positive 2. Then I'm doing my right-hand side. I'm coming to 3 from the right-hand side, and I can see that this thing has a y value. It's approaching a y value of y equals 3. So this one, can I squeeze it in there? Equals, yeah, 3. G is asking for the limit of h of x as x approaches 3. So remember, the limit, when it doesn't have a little plus or minus after it, doesn't tell me which direction from 3. So that means both directions have to be the same. So here I'm coming on the left-hand limit. Here I'm coming on the right-hand limit. What do we notice? They're not at the same value, right? It's like having train tracks that don't connect. That is bad. We don't want that to happen. It would be dangerous for people. So we're going to do DNE. Does not exist. And then what about h of 3? This is just plain Jane function stuff. Well, here's h of 3. Follow it up to see where the dot is, and that one's going to take me to 2. So this one is going to give me equals 2. All right, good job. Hopefully that made sense. If not, watch it again. I'll see you for the next video.